Hello everyone, this is Park Jun-han, and I will present my dissertation on a novel laser interference lithography and its applications. Content of presentation is as follows. First, I will present why I started laser interference lithography research. Main objective of this study is the fabrication of nanopattern cylindrical mold. Because laser interference lithography, or LIL for short, is powerful technology for large area nanofabrication, so I aim to apply LIL for nanopattern cylinder mold fabrication. For this goal, I introduced and demonstrated nanofabrication employing a novel LIL process. It was demonstrated on the planar surface and non-planar surface. And I will discuss this in this presentation. So now I will explain why nanopattern cylindrical mold should be studied. One of the most cost-effective process for mass production is local process such as gravure printing or nano imprinting. And this process requires cylindrical mold. However, most of cylindrical mold have been fabricated by directly, but require additional lapping process. Because this lapping process may cause inevitable defect, then factory continuous process is impossible. For this reason, demand on seamless fabrication process have increased. Of course, various research have been conducted for seamless cylindrical mold fabrication. Various approaches such as laser ablation, nanocoining, lithography for this goal have been suggested, but they have their intrinsic limitation. For example, direct laser interference patterning showed poor pattern quality, and nanocoining showed fine quality result and faster process speed, but contact between die and cylinder may cause damage to pattern. And E-beam lithography is a too expensive process for mass production, and the photolithography showed only microscale fabrication yet. So I applied LIL for seamless cylindrical mold fabrication because LIL have various advantages for high resolution nanofabrication because it is a maskless process and have no diffraction limit. Specifically, LIL have several strengths as follows. Firstly, process time is short. I finished the exposure process within 1 day in my study. Second, feature size is smaller than wavelength. Last, this process is continuous and seamless process. Before fabrication of cylindrical mold, I applied this process for planar substrate. For LIL process, beam splitter setup or Lloyd meter setup is typically used. However, these setups are not suitable for non-planar fabrication. So I suggest the prism-based LIL system for large area non-planar fabrication. This system uses prism as beam splitter and fiber as optical source. Because of a prism, this optical module is very compact and can be moved easily by linear stage. This is a picture of a prism-based LIL system. Optical module consists of like this stage, prism, and fiber coupler, and it is combined with several linear stages. Also, single mode optical fiber must be used for this system because only single mode fiber can transfer laser without coherence issue. Using this system, I fabricated various patterns on planar silicon substrate, and specification of used device and materials are shown in this page like this. This page shows various prisms used in experiments. Prism shape defines pattern, and it is shown in this page like this. Also, prism cut incident laser beam for more uniform intensity distribution. Changing prism, laser beam was exposed on the silicon substrate. As a result, various patterns were fabricated, and they are matched to simulation result. Left is a prism, center is simulation, and right is a SEM image of a fabricated pattern. That pattern and whole pattern also were successfully fabricated by this prism-based LIL process. Next, I tried the same procedure with linear stage for demonstration of a continuous process, and there were no big difference to previous result. In summary, prism-based LIL was suggested and demonstrated by fabrication of various patterns such as line, dot, and holes. Next, I applied this prism-based LIL for non-planar fabrication. Before this, I investigated several issues on non-planar fabrication. Total 3 issues were discussed. First issue is projection of light. Although beam intensity distribution is uniform, however, it is not uniform on the curved surface, and it may cause various defects. For this reason, I tested the LIL process on various cylinders with various diameters. 740 nanometer pitch line pattern was fabricated on this cylinder. Result on 100 mm and 30 mm cylinder was not different to them on planar substrate, but result from 10 mm and 5 mm cylinder showed difference. Pattern pitch become longer, and pattern was unclear on this cylinder. Region of the distortion was considered as light of projection, and I calculate it using this equation. This equation is derived from calculation for projection of light. Then this calculation result was compared to experimental result, and they show almost the same trend. And from this graph, it was neglectable on enough large diameters cylinder according to this calculation. Next, second issue on non-planar process is spiral beam path. Different to typical laser process, beam intensity distribution is not Gaussian in LIL process. Therefore, continuous beam moving may cause contrast issue like this. So I designed the simulation for this issue. When beam moves along the x-axis by 1 nanometer, then beam moves along the y-axis by v nanometer. And total sum of exposure dose was calculated. By this calculation, results show the contrast decrease like this. Frame 1, frame 50, frame 200, and on the frame 300, there are very low contrast, and finally, there are no contrast in the pattern. However, from the further simulation, it was confirmed that only extreme parameter cause this result. For further calculation, I used a parameter interferometric visibility. It showed the pattern contrast, and it increased like this when V increase. From this graph, we can see interferometric visibility is near to 1 when V is enough large. So I applied actual experimental condition for this simulation, and there was no significant contrast drop. Frame 1, 2020, frame 80, and frame 10,000. And we can see a little tilt of pattern from this image. It is not perfectly vertical. This tilt was also calculated like this, but it was very small and neglectable because it was less than 1 nanometer. In conclusion, this issue can be handled by enough large cylinder and proper bin size. Last issue on the non-planar LIR process is focusing error. In the LIR process, gap between the prism and substrate must be kept consistently. However, several factors such as crooked cylinder, axis misalignment, or center misalignment disturb it. So it must be compensated by additional setup, and it will be described in the next chapter. In summary, 3 issues on non-planar LIR process have been discussed, and they can be controlled by proper parameter setting. However, focusing error must be compensated by additional setup. Next, I will present experimental section for cylindrical mold fabrication. Overall process are like this. First procedure is a cylinder preparation, and next, I coated the photoresist on the cylinder, and after that, we use the prism-based LIR system to expose a laser, and last, it is developed by developer. This is a final result of a cylindrical nanopad, a cylindrical mold. This is experimental setup for exposure process. Cylindrical mold is combined with drum latte, and it rotates the cylinder. Optical module is combined with Z-axis linear stage, and it moves slowly along the Z-axis. And optical module consists of 3 parts: prism module, spatial filter, and auto-alignment system. Firstly, optical module consists of Z-axis linear stage with a prism and confocal sensor. Before exposure, sensor measures the gap profile continuously and calculate optical beam path. Finishing this process, laser is turned on, and Z-axis linear stage along calculated beam path. This auto-focusing helps to reduce focusing error. Secondly, this is introduction of auto-alignment system. Because core of optical fiber for UV light is very small, and moving optical module may cause vibration on this module. Because of this reason, beam coupling can be easily broken. Due to this reason, auto-alignment system was introduced for non-planar LIR system. System was used with conventional alignment system. This is device and materials used in experiments. Before laser exposure, cylindrical mold was coated with photoresist by spray coating method. Cylinder is chromium-coated aluminum with 1,300 mm and 300 mm diameter. Parameters in experiment is here. Input power was 100 mW, but final power was 13 mW because of several loss from optics. Total exposure time was 22 hours, and it is less than 1 day. After that, cylinder was developed with developer MAD377. As a result, fabricated cylindrical mold is here. In this picture, we can see the structural color, meaning nano pattern. Also, I observed the surface of the mold using UV curable replica and SEM. As the result, line pattern with 300 nanometer pitch was observed. Pattern width was like this, and because it is a reverse replica of cylindrical surface, so actually pattern width is 80 nanometer to 110 nanometer. It is the least magnified SEM image, and we can see its nano pattern was fabricated consistently on the large area. However, pattern contrast was relatively poor. In this page, there were 3 images. Left one and central one is a pattern from previous result by planar LIR process, and right one is a pattern on cylindrical board and is showing least contrast. I guess the region of low contrast is not coherent intensity profile. Different to previous experiment for planar substrate, I used a more focused beam and it may cause low contrast. From other literature, this idea could be supported. Also, because photoresists have a kind of threshold for exposure dose, so little change in contrast can be significant error. To solve low contrast issue, it could be considered that laser beam size must be larger than this experiment, and higher power laser or beam homogenizer must be used for more uniform intensity distribution. In a summary, various issues on non-planar LIR process was discussed and demonstrated experimentally. After that, seamless nanopattern cylindrical board with 20 millimeter length and 300 diameter was fabricated by non-planar LIR process. Its surface was observed by UV curable resin replica, and SEM images showed 300 nanometer pitch line pattern was fabricated. Here is fabrication and patent. Thank you for everyone.